All right, well, welcome everybody. So it's my pleasure to introduce Alane Suhr, who's from Berkeley, where she's a professor in computer science. In your second year now, is that right?
Yeah.
Yep. We did try to hire her here, but she decided she wanted to be there. And she was in Philadelphia for the new conference on language modeling, and we got her to pop down and give us a talk before flying back west. Alane is one of a relatively small number of people who are doing serious work in situated natural language processing. So not just multimodal data, but interaction. It's a grounded interaction, and some of that work, if you were here for her job talk a couple of years ago, you'll remember involved people playing games in situated environments and simulated environments and communicating with one another and with machines. So Alane did her PhD at Cornell, actually the New York City campus, Cornell Tech, with Yoav Artzi. And then she was at the Allen Institute for AI, working on common sense reasoning with Ye-Jin Choi. I want to commend her for doing linguistics as well as computer science as an undergrad. So that's always a good combination.
Thank you.
Thanks.
Thank you. Yeah, thank you so much. And I'm happy to take questions like in the middle if people have any questions. I'm going to try to keep it to like an hour with some time before the hour for end questions. Anyway, okay, so today I wanted to talk about the role of joint embodiment in situated language-based interactions. So a lot of us are interested, especially in the last year or so, in jointly reasoning about perception and language. So we have a lot of these vision language models that are performing very well on different benchmarks. For example, the new MulMo model from AI2 is even outperforming things like GPT-4V. And a lot of the approach here has been on scaling up models' size and training data and things like this. But these models still fail at a number of things that humans are that are pretty trivial for people. So for example, they still struggle with fine-grained visual understanding. So this is a data set that this is my very first ever paper research project, was creating this data set. This data set is called NLVR, where we have these synthetically generated images with shapes and different colors and things like this. And each of these images is paired with a statement. For example, there is a box with items of only 2 different colors and a small black triangle touching the wall. And the task here is just to determine whether the sentence is true or false. So it's like a simple, in quotes, classification task, simple to evaluate. In this case, it is false because none of the boxes have a small black triangle touching a wall. Models are still really poor at this. So recent evaluation with the GPT-4V model showed that it's getting only 59.9% accuracy. The majority class baseline, which is just to say everything is true about every image, is 55% or something like this. So it's barely above chance. They also have issues with spatial reasoning. So for example, if we have this image and we are asking a system, is the cow ahead of the person? The system has to understand what it means to be ahead, even if so from this perspective, we need to know what the front of the cow is and where the person is with respect to the front. Models are also performing quite poorly on this task with about 64.2% accuracy. Again, this is, I think, also a binary classification task of sentence truthfulness. And there's also issues with compositionality. So when I refer to some plant surrounding a light bulb, that's referring to this thing on the left. If I'm referring to a light bulb surrounding some plants, I'm referring to the image on the right. So in order to understand which of these things this is referring to, I have to understand the compositional relationship between the plants, the light bulb, and what it means to surround something. And the recent paper from maybe a month or 2 ago was evaluating specifically on this data set and find that the performance of the state-of-the-art vision language models is barely above chance. So there's a long way to go for building these vision language models. We're still definitely not all the way there. And one of the things that I propose is a big problem is that we are really focused on photographs as training data and evaluation data. So most images on the internet, which is what we end up training our models on, are depictions. Someone has taken a camera and decided to capture a scene. usually for some like communicative purpose. They want to take a photo that they'll then either use to remind themselves of an event or, you know, share with someone else to communicate something about an event or a person, place, thing. So language and vision tasks are typically framed from the like frame of reference or perspective of the photographer. There's not a lot of representation of different nuances when it comes to things like spatial relations in visual understanding in these data sets. So for example, we have this data set called spatial sense, which is tasking models with identifying the relationships between objects. For example, you know, is the dog in the water? Is the ball in front of the kid? Are the glasses on the man? Is the cloud above the mountain? And what it means for something to be in or in front of or on is really dependent on the actual objects participating in that relation and, of course, the visual context. And this kind of visual reasoning or spatial reasoning is really not well represented in the kind of data that we collect for training our vision language models, which relies a lot on images paired with alt text or other kinds of captions. Another example of this is the visual spatial reasoning data set. This is also an image text entailment task where you have an image and a caption, and you have to determine whether the caption is true or false. So to sort of dive into this just a little bit more, one example that shows sort of the limitations of using this two-dimensional representation of scenes that comes with you know, working with photographs. If we have this caption, the potted plant is at the right side of the bench. This is true. But if we were to show this to, if we were to take an approach of saying, okay, our computer vision model or our language understanding model is first going to identify, you know, the location of the potted plant and the location of the bench, and then, you know, determine whether, you know, the potted plant is at the right of the bench. In this case, it's actually not, because, you know, most of the potted plant's bounding box is actually to the left of the bench. So in contrast, maybe what we need to do is have a more a rich representation of objects. For example, you know, maybe we have this 3D representation of the potted plant and some 3D representation of the bench, and we know that the bench has a front to it. So we can reason that, you know, the potted plant is on the right of the bench because we know where the bench's front is. But this isn't necessarily going to generalize to things, to other spatial relations like in or under or things like this, where the constituent or the intrinsic directionalities of different objects are not just front, but we also have like interior or top and things like this. So I'm just sort of illustrating what we get from looking at more naturalistic stimuli and these harder reasoning tasks that don't come through when we're training just on photographs and captions that people have sort of arbitrarily written about them. So a lot of work is moving towards visual grounding in three-dimensional scenes, where our input representation to our model is not just a photograph, but an entire 3D scene, like a scan of a room or something like this. So looking at 3D scenes as stimuli gives us better, more complex, the ability to study more complex and compositional spatial language. So for example, you know, in this data set, refer at 3D, we have a reference resolution task where we have some natural language description of something in the scene. For example, the armchair that is close to the refrigerator, and the task is to determine where in that 3D scene are we referring to. So in the armchair that's close to the refrigerator, you know, in blue here, we have like the refrigerator, and then we have the armchair that's like the closest to that refrigerator. Of course, we have other armchairs, right? So we need to understand, you know, what like the closest thing means, like, and think about like proximity. So this does further challenge our models, and this reflects more naturalistic, like spatial compositional reasoning. But one of the things here that we're still missing is we're operating on like this third person view of a scene. So we have, you know, this full representation of everything going on in the room. We're not actually embodied in the scene. Embodiment is a very core aspect of like our own like daily lives. We have one body, we have, you know, only perception where we like physically are. And I think it's a very core part that's missing in building a lot of grounded language technologies. We are not photographers, like our eyes are not really taking photographs. We are observing, because we have goals in mind and we're trying to look at things that like help us achieve those goals. So there's a number of data sets that are looking at, instead of what photographers are taking pictures of, what are people actually seeing in their daily lives? Like what is our gaze focusing on when we're trying to complete different tasks? So like Ego 4D is an example of this, where you have a bunch of people completing a bunch of different tasks like walking or cooking, wearing a head cam, just going about their daily lives, sometimes like narrating what they're doing or talking to other people. And they've collected this data across a number of like regions across the world. And another example is SayCam, where there's a kid who has like this head cam, and they collect maybe, I don't know, 10 hours of data a week as this child is growing up. Just what is the kid looking at? How are they, interacting with their parents? What's the kind of language that people are using? So these are both really good examples of data that actually illustrates what it's like to be in the world as like an agent that from the first person. So I really like these data sets for this reason. So a lot of work has sort of studied embodiment from the perspective of building language technologies. And there's a number of tasks that have proposed these challenges of embodiment in like three-dimensional or situated environments. For example, the embodied question answering task is, you have some robot, in this case, it's in a virtual world in a 3D, synthetically generated 3D like house environment. Starts in a starting position, and then you ask the robot some question, like what color is the car? And in order to answer that question, the robot has to move around, navigate in the house to find like where the car would be. So the embodiment here is that the agent is able to influence its observations of the world by taking actions. So, moving closer to the outside of the house will allow it to observe, what's outside and possibly what the answer to this question is. There's a lot of work also in vision language navigation or language conditioned navigation, where we have, three-dimensional scenes or panoramic graphs, where we have sort of like in Google Maps, where we have nodes in some graph, and at each node, we have a panoramic view of the scene. And so you can traverse that graph. The task here is to navigate this graph by following this instruction, like head upstairs, walk past the piano through an archway directly in the front. And you can see now how a lot of the language people are using here is very compositional and requires understanding these spatial relations, like directly in front or turn right when the hallway ends, that sort of thing. And of course, we've seen a lot of work, especially in the last year, on developing different language agents, like web navigation agents or device control agents, or even like software engineering agents. And I would argue that these are also embodied tasks, because the agent is executing some actions in some environment such that its actions are influencing the state of the world, for example, by like scrolling on a web page or clicking a button. So in situated interactions where an agent or one or two agents is actually embodied in the scene, having a first-person embodiment facilitates egocentricity, so the ability to refer to things like, on my left is, a car, or if I go, forward to the end of the hallway and turn right, I'll see this face or something like that, with respect to the camera, so with respect to a first-person view. But I think there's something very special about joint embodiment in an interaction, in a situated interaction. And what I mean when I say joint embodiment is that we have at least two agents that are in the same scene. So they partially share observations with one another, but their observations are necessarily different because they're different agents and they have different perception. So in these multi-agent situated interactions, our agents are taking on different perspectives of the scene. And in order to communicate most effectively, we can accommodate our interlocutor, the other agent in the scene that we're sharing the scene with, by taking on their perspective, by reasoning. Yes, yeah. Oh, you have a question?
Well, you can finish.
Oh, okay. Sorry. By reasoning about what your interlocutor can see and how you can describe the world such that they're most able or more sufficiently able to understand what you're talking about.
I was going to ask you if all of the perspectives that everybody takes and what they can see as commonality.
It could be, but it could also partially not be. So we have some interesting results from another line of work that I'm not going to talk about today. I don't know when it would be best to give an example of this, but maybe I'll try now. Okay, so we have, this is like an aside from this slide, but I'm really excited about this example. So we have this data set that we're collecting of people playing an embodied video game together. I don't know if people know video games. I've learned that people who are like 5 or 10 years younger than me don't know this game, even though it's like a really popular game. Who here has heard of the Portal series? Yeah. Who here has played like the Portal 2 co-op game? Okay, so it's this it's like virtual world. It's like a puzzle game. It's kind of like an obstacle course. And there's a co-op mode where you and another person can collaborate with each other to like solve these puzzles. I think this is a really cool test bed for like studying embodied language use, because you're physically in the same environment as your partner, and you have to coordinate with each other to solve the puzzle. Like you have to ask and answer questions. You have to give instructions. You have to like sometimes teach your partner something, negotiate about what to do. And it's this, spatial environment, and this gives rise to like really, really interesting spatial language phenomena. So one particular example is a lot of the time the agents are in this big room and generally have a sense of where each other is in the room. So, let's say that I'm in this corner and I know that my partner is like behind the wall over there. I could, if they ask me, like, for example, where did I enter this room? I don't actually know which way they're facing because I can't see them. I know where they are in the room, but what we see from our data is that people will very easily say, oh, to your right. Or like, yeah, so that, to your right over there is like where I entered the room, for example. And I think that's just really cool because I don't know which way they're facing. But people are like doing this like pretty effortlessly in our data. And I think there's a lot of interesting like hypotheses on like why we're able to do this. But yeah, so you don't actually have to have full knowledge of the perspective of one another in order to do this. Yeah.
So it's crucial to have agents actually sharing the same physical space. So I can imagine, like say, I'm on Zoom right now watching this talk. I can imagine your perspective in this room, or audience perspective in this room, but I'm not really.
Yeah. I mean, that's a good question. Like, I think that we haven't had to really think about this until we had like virtual presence, like things. And I think I haven't studied this. I know that there is, I think, some work on like language use or communication, at least in like video mediated communication, how that's different from like, in-person face-to-face conversation. I don't know. I mean, obviously, I'm sorry for the people online because I was like pointing and things, and you're not in the room, so it's probably not a very good example, but for you. But yeah,
Actually, I think they could imagine.
Yeah, if they've been in this room before, they probably could imagine what I'm referring to. Yeah. Okay. Yeah, but it's a good question. And I think one thing is that people are very flexible with respect to like the communicative situation that they're in. And I think this is actually, the example I gave is a really good example of this, where we're very rarely in a situation where we can easily talk to each other, but we're actually like in the same space, but still far away. Like maybe if you're yelling across a room to someone, but I think that the fact that people are able to do this in real time, and they probably haven't had to make this kind of spatial relation before, or like very rarely, I think that's like really cool. I think that's something that we see, like people can adapt really quickly to, okay, we're on Zoom now, so we still need to communicate. We're going to really quickly adapt. One example of this that I know of is, I think it's the case, I've heard that like younger sign language users actually sign like closer to their face, because potentially because, over the Zoom era, like you had like a smaller frame. So people are adapting, people always adapt their language use. Yeah. The situation. So, okay, yeah, I will continue. So what I'm showing here is this older work. So there were a number of studies in like psychology on looking at how people refer when they have different amounts of like sharing of their visual perspective, with one another in a situation. So for example, here they're showing like two people are at this virtual table. I think they actually might have been at an actual table. And then there's these two items on the table and you have to refer to one of them. So if you're referring to the one with the X on the top left here, you might say, you know, the one on your left or the one on my right, right? But how does this change when you actually are looking the same direction as your partner? You might say like the one further back or just the one on the right. You don't have to say the one on my right or your right, right? So there's a lot of older work that studies this in these very strictly controlled settings like this one. And I think more generally, when we think about, I think this is one example of a line of work that looks at how situation design influences language use. So for example, this work was also looking at if you have a real partner that you're communicating with in real time versus an imaginary partner that you're talking to who will read your instruction or refer your reference later on. How does this influence language use? How does the relative placement of the things you're referring to influence language use? For example, you know, on the top right, you could refer to the relative like proximity, but for the one on the top left, you can't because they're the same distance from both you and your listener. And then there's also work looking at how having a multi-turn interaction for resolving these references influences language versus a single shot thing where you have to say one thing and then they have to decide what you're referring to and then the interaction is over. In general, I think one thing that's really key to a lot of this style of like this perspective on language use is when we're in these situated multi-agent collaborations or interactions, we're getting language because we have a stake in an interaction. And so when we design our interactive task to require communication, I think we get the most interesting language data. Okay, maybe I will move on to talk about what we're actually doing. So we have a new paper that'll be at EMNLP this year that I'm going to focus on for the rest of the talk. Okay, so in this work, we're studying existing systems, how existing systems use language in jointly embodied scenes. Do they generate language that's accurate with respect to spatial relations necessary to participate in this communicative task? Do they accommodate their interlocutors by taking on their perspective? For example, by saying it's the one to your right. This makes it easier for the listener to resolve the reference compared to like it's the one on my right because it's already their perspective, right? Do they understand language that's generated by people, generated by humans that are accommodating them in embodied interactions? So the task we study here is a reference game. And if you haven't heard of a reference game, there's a couple, I'll just explain it now. There's a couple of components. We have two agents. We have a speaker agent that maps from some environmental observation, so it's visual perception, to some natural language reference. So we have observations, we have reference. These are the things that we could refer to. And in this case, we have n of them. So we also have an index on which of them I'm trying to refer to, and then a natural language instruction or reference. And then a listener agent will map from a reference that's coming from the speaker agent to a referent selection. So the speaker or the listener has some perception of the environment, has the set of possible reference that could be referred to, and the reference that was generated, and then has to decide which of the references was the target reference. And communicative success occurs when, so we sample some reference from our speaker agent, we give that to our listener agent, and we are successful if the listener chooses the same thing that the speaker intended. Okay, I will give a small example soon, but I want to talk about environment generation. So we have this new environment that we are using to generate stimuli for this task in this joint embodiment scenario. So we have 3D-based environments from ScanNet++, which are these high-quality 3D scans of like interiors, mostly like homes. We will then place agents in this environment. Here I'm representing them as cameras. They're associated with a pose, which is a location in the 3D space, and the yaw of their view, which is like horizontally, which way are they facing. We sample the heights of the agents from reasonable human heights, and we enforce a couple of constraints. They have to be far enough away from each other. Their fields of view have to be non-empty, as in like the overlap of their field of view has to be non-empty. So they have to have some amount of shared visual perception. And then the speaker agent here always sees the listener, so that the speaker can always generate a reference that the listener will be able to, like, hypothetically generate a reference the listener will always be able to understand, because they have access to the listener's location. But they don't know what the listener is actually seeing from their camera. Then we will get some candidate reference. Here we're just using these spheres. So there's in this case, we have the 2 red spheres, and we also have this blue sphere. We randomly sample their locations, and then we use gravitational physics simulations to just drop them so that they come to like a natural resting point. And we make sure that all of the reference are visible to both of the agents. So we don't hide any of the spheres for either of the agents. And then from this, we will render the scene. So this is just a 2D projection from each of the 2 camera poses. All of the reference are red, except for the speaker. The speaker's target referent is blue. And so this is how we indicate to the speaker, this is what you need to refer to. But of course, the listener can't see the different blue color because the speaker has to describe which one is blue. And then we render the agent cameras as 3D human models to make it look like there's actually a person in the scene from each person's perspective. So for example, here I'm showing the 2D renders from the speakers and the listener's view. It's actually a little hard to see the speakers or the 2 agents because we make sure the lighting is consistent and everything. Do I have a way of marking up on Zoom? I don't think so. Oh no, I should have attached my iPad. I'm sorry. They're basically in the exact middle of both of these images. If you're in the actual room, here's the speaker, and then here's the listener. You can kind of see the listener a little easier. And you can see that from the listener's perspective, all of these spheres are red, and the speaker has one of the spheres is blue. And that is the target referent. So the reference game here is we sample from our speaker, we get our speaker to give us a description of the target referent. In this case, you might say on your right near the basket, given their observation, which we're denoting as OS, and the set of reference R and the target index T. Then we take our listener and we ask our listener, okay, given this reference, which of these 3 references is it most likely to refer to? So we also run inference, or we ask a human to make a selection conditioned on the observation of the listener, which is OL, the set of possible reference, and the utterance that was generated by the speaker. So the listener will choose one of these. If it's a person, we're gonna they just can click on the image. And if they click the thing that is the target, then we've succeeded. And if not, then we've failed. So success here is actually twofold. It requires the speaker to generate an accurate and distinguishing natural language description. So you have to be able to do language generation, but we also need the listener to be able to understand these references. In this case, we had a success. Okay, so we also look at a couple of different ways of controlling the difficulty of the task. The first is that we look at the differences in speaker-listener orientations, the relative orientation between the speakers and the listeners. So the example I gave earlier was, the speaker and the listener were directly facing one another. Here, their relative orientation would be like 180 degrees. If they are facing the same direction, it would be 0 degrees. And we hypothesize, similar to the older work, that this would influence the language that people are using. We also sample uniformly across bins, different ranges of this this possible set of orientations. So, for example, this is 180 degrees. Both of the agents here, which are also pretty much in the middle of the images, are facing one another. But then we also have cases where, for example, the speaker is behind the listener here. And so they're sharing essentially the same view.
And you get occlusion and everything.
Yeah, we have Exactly, yeah. Okay, and then the other thing we do is adversarial referent placement. So the actual placement of the objects could influence how difficult the task is, of course. And I'll show a couple of examples in a minute, but basically what we did is we train a model to place reference in the environment, conditioned on the set of possible locations that a referent could be in. And the observation from the speaker's point of view and the locations of the speaker and the listener. And this placement policy will give us a distribution over the possible locations of the reference. This is just implemented as a vision transformer. And the key thing here is we're training this model to actually maximize communicative failure between two automated agents. And what we're doing is we're sampling, basically we're sampling utterances from GPT-4V. We're getting GPT-4V to try to resolve those utterances, and we want to train this policy to find locations of reference that make that most difficult for the GPT-4V pair. So for example, this is a scene with random, I believe this is the random referent placement. So how might one, so if you were the speaker on the left, so the speaker's perspective is on the left. Would someone like to try to describe the location of the blue referent? The furthest. Okay, yeah.
The one at my feet.
The one at my feet. Yeah.
Oh, the one that's closer to the end table.
Closest to the end table. Okay.
I don't know what's the table called.
Yeah, no, I think that's a end table or some console or something like that. Cool. What about this one? The smallest. They're all the same size. Maybe, but I think it's pretty close in size to the one right next to it, right? I don't know. Maybe. What? Oh, you're looking at the back one. Yeah, okay. No, so the blue one now it's closer to another one.
We see something like that. You see there are two ones that close to me. Pick the one that's a little bit on the left side.
Yeah. Yeah. So it's a little harder, right? Okay. So this is just examples of like randomly placing them and then using our policy to place the objects. Okay. So we get, two types of environments here. One where we have random referent placement, one where we have adversarial reference placement, and we can see how this influences like performance between humans and agents and so on.
Are the adversarial ones sufficiently diverse for this to stay interesting? I just worry that like all the adversarial ones will all we'll go to the ballroom and just put stuff in the middle of the floor apart from any landmarks.
I mean, I think, I don't know if that's, I mean, so first of all, I don't know if we quantified the diversity. I think it is relative, like it is actually depending on the visual, like the perception of the scene. It's not just like, okay, we're going to do, an equilateral triangle in the middle of the floor or something like that always. But I don't actually know. I mean, I guess it would be a result that says we don't actually need to train a policy. We could just heuristically say like that's like the best way to adversarially generate, but I think it's still.
No, I meant the train policy.
Oh, okay.
I was just thinking,
yeah,
if it avoids putting things near landmarks because that's too easy, then the agent might not learn to use landmarks when it's possible, because you didn't have those in the adversarial set.
Oh yeah, I mean, I think you can still use landmarks. Like, I think even if it's far from landmarks, you could still say it's like closest to a landmark, right? I mean, it depends on the situation. Yeah. Actually, that's an interesting experiment that maybe we should have ran. I'll talk a bit about learning. Most of our experiments are actually just on inference of models and evaluating them. We have some evaluation on learning, and we didn't do evaluation of like if we train just on the adversarial versus the like randomly placed environments. That'd be cool. Yeah, be interesting. Yeah. Okay. Any other questions? I think this is.
It's a follow-up question, similar to what Jason suggested, at least my understanding about what he suggests. So you have perspective environment features like the landmarks, which will be probably easier for you to use. you don't need to consider perspective at all.
Mhm.
Then maybe like a very easy check is like say before and after training, you can see how much of these how many of these features I can actually use after you optimize your adversarial kind of placement.
Yeah. I mean, so I think we did some analysis of this. I'm not sure if I have it in my slides. I will talk about before training, we have some analysis on what we're calling like referential strategies. I don't want to spoil the results, but we're looking at this. Like, are the models actually referring to other objects in the scene? Are they referring to like the perspectives of the two agents? And we do have some results in the paper on what changes after training, but I don't think I put them in my slides, so I'd have to like quickly look them up. If I think we'll probably have time for that. Yeah. Okay. Yeah, so we're in order to, so part of our data set contribution is a bunch of these pre-generated scenes. Of course, you can use our code to also generate new scenes. We have this trained adversarial referent placement policy, where we're basically, trying to make it harder and harder for the GPT-4o, I think it is, yeah, it's GPT-4o agents to play the game with one another. We use 450 base environments from CNET++. We make sure that if any of our heuristics have failed, we do some like post-hoc filtering to remove them. And we have a total of like 27,000 pre-generated scenes. We also have a set of human written references for a subset of these scenes. So we crowdsourced with almost 200 workers on Prolific, English speakers who get from the speaker's perspective, need to refer to the target object. We also pair each of the written referring expressions with 3 other listeners, human listeners, guesses on what the reference is referring to. And this gives us a total of like 3,000 references for about 1,500 scenes. So on this data, and also just in general in these scenes, we're evaluating, because we're also evaluating model-based reference generation. We look at a couple of different kinds of models and their performance here. So one is a bunch of different pre-trained vision language models like LAVA. These models will independently embed images and text into tokens and then jointly process them with transformer architecture. They're typically trained on vision language data from the web. This one in particular was also trained with, I think it was like the captions were reformulated into question answer pairs. And the models are fine-tuned end-to-end, also with instruction data. So these are instruction fine-tuned vision language models. We look at LAVA, and I don't remember what the other one is. Or maybe we just look at LAVA. I don't actually remember. It'll be in a slide or two. We also look at a subset of these kind of models, which are focused specifically on fine-grained image understanding. So these are Ferret and Groma, and the way that these work to do better fine-grained image understanding, so like details of what's in an image, is by learning region embedders instead of just like tokens for arbitrary patches in an image. We also look at modular vision language systems, and or like also called maybe neurosymbolic vision language understanding systems. I like these systems. I think they're really nice. The setting here is we have some kind of natural language task, in this case a QA task, which pet is in the top left, and a visual input. And the strategy here is, instead of just putting those into a single model and then getting an answer, we actually decompose the problem into first generating a piece of code that sort of implements the natural language task, and then execute this code on top of the image. So this code is generated independently from the image at all. So we get a single program that represents like identifying the pet that's in the top left, right? So that's this generated code here. And this code calls like computer vision libraries, for example, finding the bounding boxes of all the pets, and then later processing them to find the one that's on the top left. In this case, the reference resolution task is pretty straightforward. We just have this reference, I don't know, the one closest to you, and we want to generate a piece of code that will give us a bounding box or tell us which of the spheres is most appropriate with respect to that reference. And then we also study these API-gated models like GPT-4o, where we don't really know anything or really much about the architecture, the training data, or the training process at all. But of course, we need to evaluate these models because they're performing well on a lot of benchmarks. Okay, so we evaluate several different speaker model. Oh, so we're evaluating both of these tasks, the speaker task, so the reference generation task, and the listener task, the reference resolution task. For the speaker task, we're mapping from an observation to a natural language reference, and we evaluate 3 speakers here, humans, and this is the pre-written referring expressions that we got from our data set, GPT-4o, and Lava 1.5. For the listener task, for the models, we cast this as a multiple choice task. We provide it with, okay, here are the bounding boxes of like the 3 possible reference. Tell me which one most aligns with the reference that was written. And our main evaluation metric is we're actually looking at pairs of speakers and listeners and asking, with this pair, what is the rate of communicative success? So again, every instance in our data set or in this evaluation is we have 1 speaker and 1 listener. They might be the same kind of thing, like both humans or both GPT-4o. They might be different. And how well do these models pair together under the same set of environments? So when we're looking at humans as a speaker, we're going to evaluate a bunch of different models as a listener, and that's what I'm showing here. The random chance performance is 1/3 because there are 3 different reference. And here I'm just showing on the very left, we have the performance of human listeners. So the success rate for human-human pairs is around, I think, an average of like 88, 86%. So of course, we're keeping around the communicative failures in human-human pairs because I think these are also very interesting. Like, when is it that humans are generating references that are harder to resolve? And then, of course, we have all of the other listener models. So GPT-4o is performing pretty well, better than Lava 1.5, but our best model here is actually Ferret, which is one of these fine-grained vision understanding models. And then the worst performing model is the Viper GPT model, which is the code generation one. I've also split the performance here by random and adversarial environments. So the randomly generated referent locations are in the light blue, and adversarial is in the dark blue. And in pretty much all cases, the random environments are easier to have this communicative task than the adversarial environments. Okay, so what about using different models as the speakers? So here I'm showing performance of 3 different speaker models, a human, GPT-4o, and Lava 1.5. And we're looking at the communicative success rate when we have a human listener. So a human reads one of these references and tries to figure out what the model's trying to refer to. The results on the left are the same as exactly what I showed before because it's the human-human setting. GPT-4o is significantly outperforming Lava 1.5 in generating understandable references. Again, I've separated out these 2 different random and adversarial settings. Just a brief note on these difficulty configurations that we have baked into our environment generation setup. So we verify that the GPT-4o setting that we're training on our adversarial policy on does significantly decrease the communicative success for that pair of agents. So in random environments, when we have GPT-4o as the speaker and the listener, we have like 61.1% communicative success. For adversarial environments, this drops significantly down to 57.2%. But this also replicates for most other pairs of agents. For example, for humans, we also see that the adversarially placed reference are much more difficult, going from like 90.2% communicative success to like 85%. We also do some analysis of the relative orientation of the agents. So if you remember, this is where we're looking at sort of the continuum between having the same perspective of the environment or a very similar perspective of the environment by like facing the same direction versus like looking at one another head on. And we see that increasing field of view overlap correlates significantly with improved success in the human-human interactions. So basically saying that having a different perspective makes the communicative task more difficult, which is kind of an expected outcome because it requires more cognitive effort to, figure out what it is that your listener might be seeing. All right, so here's where we're looking at different referential strategies. So what I'm referring to here is how are our speakers communicating the location of the target referent. So we split this into 4 different categories. The first is referring to these with respect to other candidates, other candidate reference in the scene. So for example, you might refer to the target here. Remember, this is like our adversarial case as the middle one in the line of objects. We can also separate this into, or we can also look at examples where they're referring to other objects in the scene. So for example, in this other example, we might say, closest to the basket. And here we're referring to the target with respect to another object in the scene. And this is going, I think I mentioned this earlier. And one thing we notice here is that both GPT-4v and Lava are like really relying on this as as their referential strategy. And this actually is not great because the models are also like pretty bad at accurately referring to other objects in the scene. So one of the reasons that Lava performs so poorly is like the success of this referential strategy is like 50%. Only 50% of the time is it like accurately referring to something via other objects in the scene.
That's not actually a basket.
Yeah, it's not actually a basket, or you still do have to take into account the other person's perspective. Like if you say it's behind the basket, it's not actually behind the basket from the listener's perspective. Of course, you can also refer to things with respect to your own or the listener's perspective. So you might say something like the rightmost one from your perspective, or the one on your right. Humans do this a lot more than GPT-4v or Lava 1.5. So we're accommodating our listeners a lot more. And then, of course, you can also refer to things from your perspective as the speaker, like on my left, where we see similar rates for GPT-4v and human speakers. Yeah, so the distribution of these referential strategies is like very different when you're looking at these automated models and actual humans performing this task. All right, I want to briefly talk about our experiments in actually improving these models. The general principle here is we want to improve these models from communicative success. So we're focusing on improving the task of reference generation. We're not using models for reference understanding anymore. We're just looking at the generation task. The overall motivation here is that empirical observations of how language is interpreted by a listener provide us as a speaker evidence of what that utterance means to the listener, regardless of what we were trying to communicate. So the experimental setup here is we have a speaker model. We get it to give us references for, in our case, like 195 scenes. In our case, we're using Lava, the base Lava model as a speaker. And then we get listener judgments of these references. So we ask a different listener to say, okay, given this reference that was generated, which of the objects is this most likely to refer to? And we will fine-tune this base model that we're sampling from originally to maximize the success rate of interaction with the listeners that we've gotten to do the reference resolution task. And we're using like PPO as this training objective, but the main thing that we're looking at is what are the different, how can we take these kind of examples and turn them into rewards or some kind of learning signal. So we're looking at different kinds of rewards that are computed from the evidence we get from listener judgments. Okay, so I'm going to show for a couple of these different rewards what this looks like. So the evaluation I'm showing here is human listener success rate for references generated by different models. All right, so again, our random chance here is 1/3. The base Lava model gets like 60% accuracy. GPT-4v gets like 66% communicative success with human listeners. And then human listeners on this subset of the data gets like 91%. The first thing we tried is what we're calling, oh yes,
But this is a single turn.
it's a single turn task, yes. So the first thing we're trying is pretty much a simple reward function, which we're calling learning from successes only, where only for examples where our listener successfully selected the intended target are we giving it a positive reward. And if there was no success, then we just like throw that example out. Across this experiment, we are experimenting with both human and automated listeners as the ones that are giving judgments during training. So in light blue is the performance of the model fine-tuned on automated judgments from a lava model. And the darker blue is coming from humans that have given listener judgments, which is always going to be, better performing than an automated listener model. Okay, so that's what we're calling LSO. A variant of this is like this positive only case, that we're calling, which is all references that we've generated from our model get some positive reward. But the target it's associated with depends on what the listener chose. So if there was a successful communication, we give this example a positive reward, pairing the reference with the intended referent, the one that the speaker intended to convey. But if it was unsuccessful, we don't just throw this example out. We pair that reference with whatever the listener chose. So this is sort of saying like, okay, if I didn't communicate correctly, it's fine. I can still learn from what the listener did in the end. I mean, in practice, this ends up just always pairing what the listener chose with the reference, because if the listener chose what the speaker intended, it's the exact same thing. So we get like very slightly higher performance with this one, probably because we're not just throwing out a lot of the data. The main thing that we found works even better is what we're calling like this pairwise preference learning setting, where for in light of communicative failure, when the listener chooses something the speaker didn't intend, what we want to do is maximize the gap in probability between what was selected by the listener and what the speaker intended. So this is sort of like a contrastive objective where we want to maximize the probability of t hat, which is what the listener chose, and we want to minimize the probability of what the speaker selected, which is just t. And so we're pairing these together. And we see that this significantly improves the model performance, and it even actually outperforms GPT-4o. As a speaker, fine-tuning on data collected from just 200 examples of references generated by a model and then just given to people who are selecting objects in the scene. Another interesting finding here, and then I will wrap up, is that we're also looking at other features of how this learning changes the model performance or behavior. For example, we see that GPT-4o, so one of these is length. So we all know that like GPT-4o and stuff are super verbose models. And this is true also for like lava models. So GPT-4o has the longest references at like 80 tokens long. Pre-trained lava is like 61. The LSO and positive only cases, when we do this fine tuning, like slightly reduce the utterance length, but only when we are training with this pairwise learning objective do we see lengths of references that really just match the distribution of human reference lengths, which is, I was like pretty surprised by this result, but I thought it was pretty interesting. Yeah. Okay. I think that's all. I wanted to, thank my students. So Dineng Tang is the first author. One of my PhD students, and Lingjun Mao is undergrad who's like doing a lot of really cool stuff too. And I'm happy to take questions.
Yeah,
Oh.
strategies portion. I was just wondering how, I'm not too familiar with this background here, if people have tried to look into the perspective before we consider the speaker's text, where instead of having it from the speaker or from the listener's perspective, you try to flip the image in a sense, where you do like projections such that your references change before giving it into consideration. Or is that like kind of just more complication sense?
Wait, so do you mean like basically having a third camera somewhere else, or?
If that's what you need in order to like flip it, or just like a way that you can have it so that like the image that you have, like the system knows that it's completely, yeah, you try to recreate the image from the speaker's perspective.
Oh, okay. So are you talking about like building like a model that would like, is it this as a strategy for getting the models to work better?
Yes, like-
Okay.
Yeah, strategy for.
Yeah,
The model does it, but you even have a different component that tries.
Yeah. exactly. Yeah. Okay. So we've thought about this a little bit. I don't know if we're going to pursue this because there's so many things that we can do with this. I mean, I think is really cool. I thought about this from the perspective of like, if you can do, all right, okay. If you can reconstruct or like attempt to reconstruct what the perspective looks like. For example, if you're a speaker and you're generating a reference, and if you can estimate what the listener's perspective might look like, then you could probably generate a more accurate reference, right? This is very related to like pragmatic reasoning theories where, you know, you take into account what the perspective of the listener is, and you do some recursive reasoning about like which reference would most easily resolve with respect to the listener's actual perspective. I agree that I think it would be really cool to see if doing like scene reconstruction would improve the performance of the models. So yeah.
A question about lens. Have you actually like looked at the I guess like the speakers like improve instructions after those fine tuning to see like whether they're actually making progress, like you know, incorporating in other people's views or like using references, or are we like only like adapting like what the speaker says to, you know, make the other language a little easier to understand? Or, you know, LLMs are very brittle in terms of like the prompt safety.
Yeah, so we did some analysis, and actually, I'm realizing I don't actually know how to find the paper on my phone. So then it has some of these results. I think the main thing that I mean, a lot of the verbosity that's like completely irrelevant to the task was removed. So these models like to talk about things like, oh, this scene appears to be like a cozy, you know, like cabin, whatever. So that stuff was left gone. I don't remember exactly what the other things we found were. I should have put this in my slides, because these are also kind of recent results that came through when we were preparing the camera ready. What was your specific question, I think, or?
I guess like are they like learning like this like you know, cozy room, that kind of stuff that seems like useless for just kind of, you know, what you age on the past.
Mhm.
Are they actually learning like some useful strategies that, you know, refer to stuff, you know, in the room, or like use other person's perspective?
Yes. Okay, I have the numbers now. I found it. So they do much more increasingly refer to the different perspectives of the agents. So when I was showing the distributions of the referential strategies before, I think it was like 11-12% of the time it would refer to something with respect to either the speaker or listener perspective. And then after the fine tuning with this objective, it's like 42% of the time it was one of the two perspectives. Yeah. So it seems to be incentivizing like referring to things with respect to like the agent perspectives.
Regarding how people describe situations to, let's say, listeners. And in those experiments, not fully sure, but maybe you felt say, oh, another listener, which is a human or a machine trying to interpret these. Do you think there will be differences if you tell the human speakers whether the listener is a machine or a human, that in fact how to describe these things?
Yeah, definitely. So one big challenge I think all of NLP now is people, okay, it's always been a challenge, is that people change how they use language depending on the situation they're in. I think it's especially difficult now because we're now adapting not just to other people, which we have been for, you know, forever. We're also adapting to things that are kind of like language users, but not exactly. And so we're also constantly adapting our expectations of what it could mean to be a language user and like how accurate things are. These things make idiosyncratic mistakes that like a human would never would. So we have to adapt to that. We have other work that shows not exactly the question of like telling someone whether it's a human or a machine, but shows how people are adapting when they're interacting with a machine in a grounded scenario like this. For example, people tend to like simplify their language use.
They would try or try to make it more simple for a robot or a machine if you tell them, oh, you're telling a robot to, access this object or that object. And if they change their language a lot from how they would just casually
Yeah, I don't know. I mean, on the one hand, maybe my hypothesis would be that maybe they would be more detailed in their description because it gives you a bit more redundancy and like, yeah.
So I was wondering if there was any related work, or do you think there's any value in having a setup that considers many speakers to one listener within one environment, or maybe having a speaker that is adversarial, like giving false information, if there's any value in that?
I mean, so the multi-speaker to one listener scenario, I'm struggling to think of like a naturalistic like setting of that. But the sort of flip thing where you have multiple listeners in different perspectives, I think is very, very interesting, because when you're talking to an audience of more than one thing, you now have to reason about like a bunch of different people's perspectives, and it makes the task like a lot harder. So I mean, I think that's definitely worth looking at. The sort of adversarial case, I think, can also be interesting. And then this is sort of leading into work in like emergent communication. I don't know if people have seen this line of work, which is like you pair two agents together and there's some like high level like objective that they need to fulfill, and the latent thing there is like, what is the communication protocol? So there's some work in that along those lines. That's the keyword I would look for, is like emergent communication. Cool. Yeah.
I'll just ask a left field question just for fun. So, like some other people, maybe chime in, one of them, you're working on reference to physical objects. People in pragmatics often do that, like RSA. So you're describing, you're giving a noun phrase and you want to pick out the object. I am guessing that that's not only because it's one important problem, but just because it's easy to score. And I wonder whether you think that there's any hope for getting beyond that setting. Like, oh, there's that recipe that we made before. What was it?
Oh yeah, yeah.
It's also a noun phrase, but
it's
the
true.
kind of grounding, the way that you discuss it would be very different. And then there's lots of other kind of things like collaborative decision making, which is so a couple of people I worked with on that at Berkeley.
Yeah. So a couple of thoughts come to mind. One is is that we can still study these grounded things with things that are not just noun phrases. So one example would be like instruction following. You're still in the same situation and it is still difficult. Like, it's not addressing this problem of like reference to more abstract concepts. But that is also another setting where you have more complex, like the model needs to do more than just like pick out an object. There's more constraints, for example, like maybe you have to go a certain path or whatever. So that is like a slightly more complex version of this task. On the side of like reference to things that are maybe not like physically there, or like reference to actions that you can like physically take right now. I think one thing that people are really good at is, and one thing that language is for, is like multi-turn communicative like repair. And so if you refer to, the recipe we made earlier or whatever, and I have some uncertainty about this, I can always ask like a clarification, or even, I mean, we do so many interesting things. Like, I could be like, yeah, like, so there's back channels are also a way of doing this, like confirming that you understand something. So language is very much built around the fact that we might have uncertainty about these kind of references or things that are more abstract than just references. And the fact that we're able to do that, the fact that we have this multi-turn set scenario means that we can do this. Obviously, this is not a multi-turn scenario.
My question was really about, can we build scenarios that make it possible to study this
Yeah.
stuff that everybody knows happens?
Yeah. I mean, so I'm really excited about the Portal game stuff that we're working on, because I think these kind of things come through there that they don't in these very tightly controlled settings. but we still need to figure out a way to like figure out how to get around this data because it's like very complex. And so that's, yeah, something I'm interested in.
Well, maybe like the follow-up stuff, like nothing about reverse again as like the downstream task, but something that you first naturally already tasking. Like that you want to fulfill. Then you refer to like that recipe that we implemented or whatever. So I guess if you downstream task is collaboration, I think naturally different kind of referential task will be and then maybe like the module. Like if you have like a overcooked game for example,
Yeah.
you have I don't know if people know overcooked game, but basically like a 2D environment where people can like cook.
Yeah.
And then that kind of recipe reference can come up.
Mhm.
Yeah, I mean, when I mentioned the recipe, it wasn't specifically about cooking. It was referring to an imperfect memory, and you and I may remember it differently. So this is maybe not that different from occlusion, or something where our sensory perception is noisy.
So one other just cool thing that happens in this portal corpus is, and I mean, I'm sure everyone's experienced this before, is you can refer to things completely incorrectly and understand what each other is referring to. So I can refer to like the ball as the portal. And if it's salient enough to both of us, and we know that it's salient to both of us, it's fine, doesn't matter. So this is like another example where it's like, if we maintain this common ground of like how each other is like understanding language, then we can be very sloppy and it's totally fine. Yeah.
Okay, well, let's thank Alane again.
Oh, is there a question? Oh no, I think I might have missed questions on the Slack. Oh, I see. Okay, never mind. Thank you, everyone.